Hi, welcome back. We're up to Lecture 7, Segment 3. The topic here in Lecture 7 is an introduction to regression. And we've already given you an overview of regression and talked about how to calculate the coefficients. I now just want to review some of the assumptions underlying a basic linear regression. Now, it turns out that the assumptions underlying a simple linear regression are almost identical to the assumptions underlying the correlation analyses that we did last week. So this segment will be quick and pretty easy, and basically a review of last week's assumptions underlying correlation analysis. So the first three assumptions are, one, that we have a normal distribution in y, the outcome measure. The second is that we're looking for a linear relationship between x and y. Again, later in the course, we'll deal with nonlinear relationships, and there are certainly ways to handle that, but for now, as we're starting out, we're just going to deal with normal distributions and linear relationships. And then again, remember, we have this assumption of homoskedasticity, which I'll show you again in the scatter plots. Let's not forget as well, just like with the correlation analyses, we assume that we have reliable measures of x and y. Remember, if we don't have reliability in x and y, if they don't correlate with themselves, then they can't correlate with anything else. So we need to have reliable measures. We need to have valid measures for our arguments to make any sense. And we need to have random and representative samples. But I covered all of that in the context of correlation. So let me go back to these first three. Normal distribution in y, the linear relationship, and homoskedasticity. When we covered these in the context of correlation analysis, all we did was basically eyeball histograms and scatter plots. We looked at the histograms for normal distributions. We looked at the scatter plots for relatively linear relationships. But we can do better than that. We can actually do some statistical analyses to evaluate these assumptions. And the way to do that is to save the residuals from a regression analysis and then start to investigate those residuals. And this is a really important exercise that we'll do over and over again, especially as we go into multiple regression. So I'm going to bring back this classic example of Anscombe's quartet because it's just such a pretty and elegant example. So remember, the correlation between x and y in each of these four data sets was exactly the same. Well, of course, it turns out then that the regression equation, if we predict y from x, is going to be exactly the same for all four examples in Anscombe's quartet. It's one of the reasons why he created it, was to show that you could get the same exact outcome in a regression analysis from those four very different looking data sets. So here is the output of a regression analysis. The regression constant is 3 and the slope is about 0.5. If you go back and look at the scatter plots, you see the intercept indeed is about 3 and the slope indeed is about 0.5 for each one of those. But clearly, only the first one on the upper left satisfies the assumptions underlying a linear regression analysis. So how can we do a more sophisticated statistical analysis to test those assumptions? Well, to test them, we can save the residuals. And this is easily done in R. We're going to do it in lab this week. But remember, for each individual, we're going to have a predicted score and we'll have their actual score. So it's a very simple step to just save the residual. We can then look at those residuals as a function of the x predictor variable. So we can construct new scatter plots where x remains on the x-axis, but now let's put the residuals on the y-axis. And here's what it looks like with Anscombe's quartet. The first model on the upper left, the first data set, This is ideal. This is the kind of thing we want to see when we save residuals and plot them as a function of x. There's virtually no relationship between x and the residuals. They're independent. And the residuals, some of them are above 0, some of them are below 0. That indicates homoskedasticity. So this looks great. That's exactly what you want to see. Otherwise, if you see that there's a relationship between x and the residual, as is the case in all the other examples, then you know that you have some sort of measurement error in x or some sort of confound in your study or in your model, because x is somehow related to the residual. And you'll see that if you plot the residuals as a function of x, as we've done here. So you see they're not linear relationships across the board, but they're clearly relationships. So each of these other data sets indicate violations of the assumptions of a linear regression analysis. It's only this first one that satisfies the assumptions because the residuals are not a function of x. So if I took the correlation in this, it would most likely be right about 0, flat line. Some are positive, some are negative, again, indicating homoskedasticity. So to wrap up this very short segment, again, it's pretty much a recap of the assumptions that we looked at when doing correlation analysis. Most importantly, normal distribution in y, linear relationship between x and y, homoskedasticity, and the best way, most sophisticated way to test those assumptions, see if we violated them, is to run the regression analysis, save the residuals, and then start to examine the residuals as we did here, for example, plotting them as a function of your predictors, in this case, just the one x variable. And what you're looking for is no relationship at all. They should be independent. If they're not, that indicates you have some sort of dependency between your systematic predictor and your unsystematic error, which indicates a problem and a violation of one of the assumptions.